So you guys have your final exam on Thursday in class. You should now have all the materials in hand to get prepared for that. I've posted homework number 12 solutions as of yesterday's deadline. I've left the problems, so as those of you that were in class on Thursday know, I knocked off a few topics. So we did not get to the Doppler effect or beats in class. Ran a little bit short, and so I omitted those topics from the homework. I did not delete them from the WebAssign outright. I just set them to 0 points. That way you have the problems for reference in case you ever need to learn those few things. You have both the homework problems, and I've also left them on the solutions. I would say particularly the Doppler effect may be of some relevance. It has a lot of medical applications. Let me just give you a 2-second synopsis on the Doppler effect. So if you have some source of sound, that's supposed to be a person with their mouth open. If you can't tell what that's supposed to be. If you have a source of sound and you have an observer of sound, or this is anyway really, but this is the observer. The key to remember is that if the source of the sound and the observer of the sound, if the distance is decreasing, so if they're getting closer together, then the observed sound will be larger than that actually emitted by the source. So source and observer. So you will hear an upshifted sound. Basically, you'll experience the crests faster than you normally would because the distance is closing. And if this distance is increasing, so the distance is increasing, so they're getting further apart, then you'll observe a frequency that's actually lower than what's being outputted by the source. This gives the rise to the classic thing where you're standing on the street corner, a car drives by really fast, laying on the horn, and you hear, right? You hear a pitch shift. It's not just about loudness. It's a higher frequency when they're coming toward you and a lower frequency when they're going away. So this is also how you get stopped for speeding. It's because a car or a policeman points their radar gun at you. In that case, it's light and not sound, but this happens with all waves. And if they bounce something off your car and it comes back upshifted, so the frequency they observe coming back is high enough, then the distance is decreasing fast enough, they can deduce from the higher frequency that they observe that how fast you're going, and if that's faster than the speed limit, you get pulled over. Okay. So this is a lot of applications in medicine. So that's basically the rule of thumb to remember. If the distance is decreasing, you'll hear a higher frequency, and if the distance is increasing, you'll hear a lower frequency. There's an equation for that. There's ways to pick the signs in those equations to account for this. That's my 2-minute kind of synopsis of the idea behind it. And not that I'm going to test you on this in any way, but I feel guilty that we didn't get to it because it is more relevant than some things for you in the future. So again, Doppler, shift, and beats will not be on your final exam. I'll leave it to you to make sure to omit those things from the final exam practice materials, which I posted before I knew that I wouldn't get to these. So cross these items out on the final exam study checklist. There are a few problems, I think maybe even just one problem on the final exam practice problem set that is relevant to this, which you should omit, in addition to some other stuff there that is already written as omitting, because I already knew at that point I wouldn't get to it. We didn't get to much thermo, which is the next topic after waves. We didn't get to any thermal, actually. And the reason why I don't particularly care is because you'll see most if not all of it in Gen Chem. Gen Chem 1 or Gen Chem 2, so you don't need to see it twice. That's basically just because the physicists and chemists don't coordinate what they're teaching, so I leave off stuff that I know you'll see in other classes. So again, the stuff is all there as a resource for the future. I've also posted some MCAT resources, just general resources for the future, but make sure you know what is being tested and what's not being tested on your exam on Thursday. Okay, so as far as what to expect, you're obviously going to have an exam of exactly the same length as the previous ones, but it is worth more because it's drawing from a larger pool of material. This is going to be somewhat cumulative. So basically, you get rewarded for demonstrating a broader knowledge base from the entire course. So here's how it's going to go. Still same format, multiple choice question section, long answer question section. The two long answer questions, if I'm feeling particularly uncreative, I'll put one question on old stuff and one question on new stuff. That means one question, which will be some combination of exam 1 or exam 2 material, stuff you've already been tested on. And then the other question will just be something from homeworks 10 through 12, so stuff you haven't yet been tested on. If I'm feeling more creative, I'll just shuffle them all up because that's more interesting and demonstrates a kind of more deep thinking. So it'll still be about that ratio, 50% old, 50% new, but I'll try to feature some of each in each question so you can kind of pull things out of your toolkit and know when to use them appropriately. So that's the long answer section. As far as the multiple choice question, all I will say is that it is cumulative, but emphasizing the post-exam 2 material. So you can read the tea leaves however you want, whatever that means. You can try to anticipate how many of each type of question there will be. If you can figure that out, I don't even know. I don't even count them when I'm writing the exam. I just go by feel. I go by, it seems like it's cumulative, but emphasizing post-exam 2 material. So that's what to expect for the multiple choice questions. As far as how to approach studying, what I would say is for the post-exam 2 material, that means homeworks 10 through 12, you should study those and know that stuff in as detail as any midterm. And then for the older stuff, exam 1 and 2, I would suggest using as a starting off point the actual and practice midterms. So at this point, between the multiple practice midterms I posted and then the actual exam that you got, you can look through those and see patterns, and you can tell what it is that I find important and what I tend to ask about a lot, and what things don't appear very much. Okay? So my testing style is not to do the old switcheroo, like where, oh, I didn't ask you at all about that on the midterm, so here's my chance on the final. I'm not that kind of tester. You should look at the actual midterms, see what are the big important things. Those are the same things that you should focus on for the final. So if you're going through the midterms and you feel pretty comfortable with that, you don't necessarily have to go through and do every single homework problem on that topic, but look through the midterms, see what might be your weak points, and then supplement from there with homework questions, and above all, extra practice problems from the textbook are always helpful because I kind of feel like once you've done a homework problem, it's somewhat spent. If you go and do that again, you're just practicing math because you already remember how to start the problem, so it's more just, at that point you're practicing algebra. So it's really important to look at new, fresh problems all the time because the physics is often the first thing you write down, right? You read the question, you pick a technique, you write an equation, physics is done, now you're just solving for something. Okay, so that's kind of the format, what to expect of the final exam. I've had several emails already from people that were kind of asking for more elaboration, and I've kind of said, well, at least ask me in front of everybody so that everyone can, for maximal fairness, get the same information. So if anyone has any further questions, I will either say I can't answer it or answer it so that everybody can hear it. Yeah?
There's another question about the grade distributions. You're curving the class itself?
Correct.
So you're taking the curved exam grades and then putting another curve on top?
No. So the curved exam grades, those are just like to give you an idea of how the curving works, but all the raw grades are getting put in together, and then that gets curved the same way as I did that kind of unofficial exam curve. So the basic thing is, when I give you those grading summaries after every exam, what that represents is if I were basing the entire letter grade of your class for the class on that one exam, here's what you'd wind up with. It's that same technique that I use for everything. So a common mistake again is say, I'll take my 99% homework average, I'll take that raw, I like that number, and then I'll take all my curved exam grades and I'll just average all those together. So that is going to overestimate your grade because you're basically cherry picking where you want the curve and where you don't. So everything gets curved together.
Including the homework.
Yes. And you will always wind up with a higher grade than what your raw percentage would indicate. But if you are just cherry picking where you're going to apply the curve, that might lead to an overestimate. I know that the post-bac homework average is very high. I think it checked and it was like 98%. The way that gets compensated is where the curve is set to. So I set the curve for you guys generally around B+, to recognize the fact that you're already achieving a very high homework average. And then the curve is really to help with bringing up the fact that if you factor in exam scores, your raw average may end up being lower. So I'll bring that up. Okay, any other questions? Just format, topics, logistical, before I get into the actual material itself? Yeah?
How do we find out what we got on this line?
So I'll put a notice in WebAssign, but I guess that's a good point because WebAssign will not be available shortly after the final. So again, if you want any course materials, save them locally before that. So that means in the next couple days. Also, I guess if you want your, well, first of all, your final grade, don't email me for that because if you don't see it posted, I haven't finished it yet. Basically, the turnaround from when I calculate final grades to when they're up and available for you is like less than 24 hours. But if you're interested in your final exam grade itself, you can email me for that. Basically, send me an email anytime. I file away in a special folder, and sometime, usually several weeks after you've gotten your letter grade already, I have enough time to send out that information. And so, don't email me for your final exam grade thinking it's going to be some kind of advanced preview of your letter grade, because it's not going to come in that order. So if you're just legitimately just curious or whatever about your final exam grade, I will get that back to you. So just let me know that you want that. Usually I have a kind of a form email ready to go where I send you your raw average, your curved average, your class ranking, and your final exam grade. Basically, any kind of statistical information you might be interested in is there. But that's something that I need to get all of my classes graded and submitted and everything like that before I can start sending out, the hundreds of emails that entails usually. Any other questions? Yeah.
Can you post the estimation table for
The estimation table? What is the estimation table?
like in each exam you show estimating your performance section?
Well, you can do that yourself anytime because the course average and standard div are available.
Oh, is it?
Yeah, you can click on grades. I mean, if you apply that to just your homework, it's going to look like a curving down. I mean, how much can I curve something that's like a 98% average, right? But the point being is that when you throw in everything into the pot raw and you apply the curve, it will raise your grade. So it will bring it up substantially from whatever you got raw. So again, if you aren't accustomed to being in a curved class, basically if you are the average student in this class, I've done lots of statistical analysis, and the average post-bac student is about a B+ student relative to undergrads, which are usually about a C+ student. And so basically I try to triangulate to make sure that you would wind up with the same letter grade you would if you took this anywhere, okay? Even if you were dominating over a bunch of undergrads who don't know how to study it, okay? Any other questions? Okay, so what I'm planning to do today, just kind of zoom out, big kind of forest for the trees kind of perspective, draw some connections between perhaps different topic areas that you may not have seen before. So I'm not necessarily going to go in linear order of what I talked about in the class, but more having the benefit of hindsight to be able to group certain things together. So feel free to jump in at any time if you have a question on what I'm saying. But otherwise, I'll just kind of give you the broad strokes, hopefully give you some kind of scaffolding on which you can kind of hang your studying and your brushing up and stuff. So we had basically three major topics in the kind of mechanics: the force method, the energy method, and momentum. So if you are competent in handling those methods of solving, being able to pick out which one to use in any given situation, you're in very, very good shape with the majority of this class. So I guess let me talk about that first. First of all, with force, at the heart of all of it is Newton's second law. So it basically says that objects don't accelerate spontaneously, they accelerate because a net force from the outside world is applied to them. And how much they accelerate will be also relative to their intrinsic resistance, called inertia, which we measure by mass. So things that are good about this method: it can calculate the time it takes to do things. If you're asked for acceleration, obviously by itself, then this is your only method. But the annoyances of it is that it requires handling vectors appropriately, which can be a little bit of a pain. You got all your SOHCAHTOA stuff and setting your components and all that business. And for us, our tie-in from acceleration into the constant acceleration equations, where we can find out about displacement, velocity, acceleration, time, so on and so forth. It's right in the name, constant acceleration, right? So constant acceleration is really our only roadmap to discussing the kind of subsequent kinematics of it. And so that's going to require that the net force be constant as well. And so you have to be fairly certain that the outside environment, whatever net force it's going to apply, that net force has to be unwavering with time. And that is, in many situations, an unrealistic expectation. So we not only have to deal with vectors, but we also have to depend on the net force being constant in time. So if that's not true, we move over to energy. Energy can handle constant acceleration, and it doesn't blink an eye if the acceleration is some incredibly complicated time-evolving thing. So we had these roller coaster loop-de-loops and all this crazy stuff where the acceleration is nowhere near constant. Energy method could care less. It handles it just the same. So things that we do give up, of course, the one thing we give up is the time to do things. And when we were doing our roller coaster loop-de-loops right around that time period in the class, we were talking about a bunch of different trajectories, all of which could result in the same final velocity, but which take very different times to occur. And the energy method doesn't touch the time aspect at all. The master equation, of course, for this was this equation. By the time we wrote down that equation, we had already at that point decided that E wasn't going to stand for all energy of any form in the universe. E was a very specific subset of energy called mechanical energy, which came in two varieties: the energy that you can see and the energy you can't see. So kinetic energy is energy due to motion, And potential energy is energy that's stored up that could come out, but is stored or hidden for the time being. And then, of course, we had our in and out valve non-conservative work, which was kind of our kind of connecting to other energy forms that we don't want to really touch in this class. So, for instance, our major culprit was friction. Friction takes energy completely away from mechanical, sends it to heat. You can calculate the work done by friction, but you don't need to worry about, well, now it's heat. What do we do with that? We just say it's gone. So common non-conservative works, friction. Another common one was we had positive non-conservative work coming in from biochemical sources. So if we had a person pushing on something, that's the way that the mechanical energy of the system can increase. And of course, in many systems, the non-conservative work was zero. So basically, the system is not connected to any foreign energy forms that we can't really bring into the fold. We're just trading back and forth between kinetic energy and potential energy. And I guess while I'm on the subject of energy, I can remind you that by the time the course was over, we had two different forms of kinetic energy, translational and rotational. So translational kinetic energy is when an object is somehow moving through space. So it's moving from one location to another. And rotational kinetic energy is when it's rotating. That can rotate around the center of mass, or in the case of a pendulum, it can rotate around another point. But the point is it's rotating in place. Whatever the pivot is a fixed point. So translational is when the whole thing is moving somewhere else. One of the most important applications of this was when we had rolling. So remember, when you're rolling, you have both kinds. So when you're rolling, you have rotation around some point that happens to be the center of mass, but that point is also itself moving, and so you have both forms of energy there. And I would say probably one of the most useful relationships, which again is not available on the equation sheet, so if you want to use it, you have to derive it for me to get full credit. Remember, when you're rolling, the rotational kinetic energy is squiggle times the translational. And squiggle, again, is the numerical factor in front of the rotational inertia. Other things that are useful for rolling, remember that rolling, you can move across a surface that is far from frictionless and yet neglect the energy loss because you're rolling and not sliding. So again, know how to derive this, and then you're going to want to use it if there's a rolling problem because it greatly expedites the calculation. The potential energy, we looked at two forms in the class. Two places that can store energy, one of which is by being above the ground, however you define that. So gravitational potential energy, MGH. And then you can also store energy in a spring. If you take it away from its happy place, you either compress or stretch it from its equilibrium, you can store energy there. One of the kind of touchstone problems that you might look at was that gigantic pinball machine problem from homework 10, because that was one of the problems that included all four of these, and you had to manage them appropriately. So that's energy, and I guess it's worth pointing out that this originally came from the work energy theorem. And the work energy theorem originally came from building it off the back of Newton's second law. So really, these first two things really are both built off the same law. F net equals ma is a giant in this class in terms of how important and pervasive it is. Really, the only difference between the force method and the energy method is that they approach things from a different perspective. So in forces, you approach them by identifying forces, vector forces, calculating your net force, calculating your acceleration. And then in energy, you're dealing all with scalars, and you're looking for conserved quantities. Okay. I guess while I'm on the topic, I did this a little bit backwards, but let's talk about all the forces we've seen. we introduced most of them up front, but we have introduced kind of scattered forces here and there throughout the rest of the semester as well. So I guess let me catalog all the forces we've seen. Is there a question?
I was
Yeah.
just wondering when you're talking about for rolling and kinetic energy rotational squiggle, are you talking about like inertia or like phi? I was just wondering if you could flesh that out.
Yeah, I mean, well, if you look back in your notes to where I talked about this, the rotational inertia for round things is always some number times the mass times the radius squared.
Okay.
So that's what squiggle is. Are there any other questions before I move on to kind of talking through some forces? Okay, so let's back up. Talk about forces. I'll name the force. I'll put down the rule for its size, for its direction,